actually, you guys, we did this. We did the first part of this problem. So you should have this in your notes from last time. Okay? You have a couple of homework that are due on Wednesday that do this exact same thing. Notice if I was going to draw a picture, and I can't remember if I did this on Friday or not. Okay? But if I was going to draw a picture of this, okay, I would draw... Okay, it looks like looks like isopropyl alcohol. Remember I told you I call it IOH. Okay, is being dissolved into water. The mass of the IOH, that's the solute, is 46.87 grams of IOH. And it says that the volume of solution is given 300 milliliters of solution. Okay, so with that same situation, you're supposed to answer two questions. In Wednesday, we did this one. You're supposed to come up with the molarity. And one of the things, and this is a hint for the homework that's due on Wednesday, if you're ever supposed to come up with molarity, I really think that you should remind yourself what that means. In this case, it means moles of IOH per liter of solution. Okay, and then the next two questions, basically, these go together. It basically says, can we come up with mass percent IOH? And again, what does that mean? Mass percent IOH means grams of IOH, mass percent isopropyl alcohol means grams of IOH per 100 grams of solution. So that's where we need to pick up. And yes, you can do that if you're given the density. So density down here, I'm going to unpack it. Naked number. Density down there, remember the symbol for density is rho, so that's density. So when it says 0.975, it means 0.975 grams of solution per milliliter of solution. That's what that means. And I'll show you how we can use that to get to weight percent. All right. So we did this on Friday. You guys are losing a little bit of points out there now, again, for not showing your molar mass calculations. You want every point possible on your test. If you put it into, if you use the periodic table and take 3 times the decimal number for carbon plus 8 times the decimal number for hydrogen plus 16.00 the decimal number for oxygen, if you put that in your calculator, you have to show it. Even if you're Rain Man and you don't have to use a calculator to get the molar mass of isopropyl alcohol 60.09 grams per mole, you still have to write it down, because most of us do. So like I said, we did this on Friday, and then the next thing we said, to get the molarity, we want moles per liter, but we can start with grams per milliliter and just fix both of those. So if we use, next term I used was the molar mass. I used the flipped version of the molar mass. The reason is so grams will cancel and we'll be left with moles of isopropyl alcohol per milliliter of solution. Almost done. We got to fix the bottom. We can do that by putting 1,000 milliliters over 1 liter. Round it to 3 significant figures, because that's what we're allowed right here. Okay, 2.60 moles of C3H7OH, or moles of IOH per liter of solution. Feel free to abbreviate things. If you're working a problem, you're like, dude, I don't want to write that formula for that thing. Well, then abbreviate it and tell me what your abbreviation is. Okay, so you'll probably see this written as 2.60 molar C3H7OH. It means the same thing. By the way, also I'm seeing a little bit of, remember the abbreviation for mole is MOL. It makes a difference because actually folks who are using a lowercase m for the abbreviation for moles, the lowercase m is abbreviation for something else. Just trust me. All right. So let's look at the last part of it, where we're supposed to come up with mass percent. Okay? And like I said, I really would encourage you, if you're mulling around a problem like this on your test, you know, calculate the mass percent. If you're mulling over how to come up with that, okay, write it down. What does it mean? Okay, mass percent. It means, in this case, grams of IOH, like I said, per 100 grams of solution. And if you go back to the original problem, you have grams of IOH per milliliter of solution. So somehow you need to get in the denominator from milliliters of solution to grams of solution. And we can do that with the density. So this goes back to the original problem, 46.87 grams of isopropyl per 300 milliliters of solution, 3 sig figs for that. Do you see where we can actually use the density? We want grams to cancel. And the other thing is, I wrote it a minute ago, but I really would unpack that. I cannot use that number just like that. Anytime you see a per like that, okay, you should be thinking divisor. Okay, that is the density unpacked. So when I unpack it, I'm like, oh yeah, I can see that. So I want milliliters of solution to cancel, and I want to be left with grams of solution down the bottom. Do you see where if I flip the density, that is exactly what's going to happen? So that next term is the density, the inverse of the density. This pattern for this problem will get you in down the road in, was it 107, 109? The problems that are coming up. So now grams of, no, grams don't cancel. Now milliliters of solution will cancel. And remember I had a slide before that says be careful. Grams and grams don't always cancel if they're different things. We have grams of isopropyl alcohol and grams of solution. So we're almost done. That would give us a ratio of grams of isopropyl alcohol per grams of solution. But we want grams of isopropyl alcohol per 100 grams of solution. So we want that. That's what we call parts per 1. So in 1 gram of solution, we have 0.160 grams of isopropyl alcohol, 3 sig figs. So if that's parts per 1, that's actually what we call mass fraction, that 0.160. So to go to parts per 100, we simply have to multiply by 100%. So keeping it 3 sig figs, that's 16.0% by mass isopropyl alcohol. So this sort of problem, you can get to the weight percent if you're given the mass of the solute, the thing you're dissolving, the volume of the solution, and the density of the solutions. Okay? All right. Homework problem or homework slide. So these will be due on Wednesday. So remember, anything we cover is fair game for your test on Thursday. Anything that I am not covering is not fair game for your test on Thursday. So let's see. Let's take a look at what these look like. 107 and 113. Where'd you guys go? There you are. Okay. So you'll see how similar these are to the ones we worked in class. So instead of isopropyl alcohol, it's sodium chloride. They give the mass of sodium chloride. They give the volume of the solution. The two things you're supposed to calculate is just like the problem we did just now, Friday and today. You're supposed to, of that same solution, come up with two things about it. What's the molarity and what's the mass of NaCl, mass percent of NaCl. Notice they do give the density of the solution. So for the first part, to calculate the molarity, I put it there in purple. Remember, what does molarity mean? Well, in this case, it means moles of NaCl per liter of solution. Okay? Well, we have grams of NaCl per liter of solution, so we know we can get from grams to moles using the molar mass of NaCl. In orange, I said show this calculation. Okay, so basically, you're going to start with that 133 grams NaCl over 1.0 liter of solution, which is what you were given. You're going to use the molar mass to get to moles of NaCl per liter of solution. That's the first part. And the second part looks like this. Remember what weight percent means. It means grams of NaCl per grams of solution. We can use the density to get there, just like the problem, pretty much like the problem. We have one more term we need to worry about. The problem we just did actually had volume in milliliters instead of liters. So I would go 133 grams NaCl for 1.0 liter of solution. My next term is I would fix liters of solution into milliliters of solution. Why? Because density is milliliters of solution per grams of solution. Okay? And then my third term would be density. I guess I should add something. I'm not going to turn it into a run-on statement, but I'm going to put a colon. I'm going to say multiply by 100 to get percent. All right. And then the next one's like the same way. In fact, it's even the same solute, so you don't have to calculate the molarity. Wait, yeah, it's NaCl. You only have to the molar mass. You only have to calculate the molar mass once, but it's like the same. Oh, no, it's not. Oh, okay. It is different. Okay. To work this sort of problem, I'm going to draw a little picture over here. Notice in this case, you are simply given the weight percent NaCl. So it's 5.88% NaCl. What I would do for this one is to unpack that. What does 5.88% NaCl mean? It means that there are 5.88 grams of NaCl in 100 grams of solution. That's what that means. 5.88%. What does it mean? So in this case, we are after molarity, just one problem. What is the molarity? Okay. So what we're after, question mark, is moles of NaCl per liter of solution. So what I would do, actually when I'm working this problem, is I would go ahead and start with this. I would start with the weight percent of the NaCl. And 5.88 grams of NaCl, but I would start with the unpacked version for 100 grams of solution. And do you see where we can use the molar mass to get to moles? Then I would use the molar mass. The molar mass of NaCl will get you to moles of NaCl per 100 grams of solution. And then my hint is to use the density. I'll just write the Greek letter rho. Use the density to go ahead and get instead of grams of solution, get liters of solution. And I guess one more hint somewhere in there. You can either do it on the end, or you can put it right there if you want, but you are going to have to, and I'll go ahead and say which way it'll be, you are going to have to use this 1,000 milliliters over 1 liter, somewhere in there. Now, when it comes time for making up your test that you're going to take Thursday, this does not look like the type of problem I probably will put on there, but it's a good one. And it's homework, so it's points. Okay, so those are my hints for that one. Really, to work any problem, it's like I've been saying all semester, you know, it's kind of like playing jigsaw puzzle, where you write what you know about the problem, and then you kind of think about what you might add to the problem, okay? You think of what you have and where you want to get to. So that's really kind of the nature of working chemistry problems. So like I said, we're going to go ahead and skip to part 4. Just because we can. The part we're skipping actually is a good part. It's called dilutions. The topic of dilutions. But what I want to get to is
aqueous solution stoichiometry.
Yes, aqueous solution stoichiometry. And I think we're only doing like the first 10 slides or so for this. The outline for the test on Thursday that I gave you the other day, the last or the second to last, actually this is, the last or second to last problem on your outline is this topic. So there will be one of these on your test. Perfect. Yeah, there's like 6 things, right? Item number 6, aqueous solution stoichiometry. Smiley face. Okay. So we'll do a few, I'll assign a few, and we'll call it a day. So aqueous solution stoichiometry problems combine the 2 things that we covered in this unit, 2 of the things we covered in this unit. That is stoichiometry and kind of how to use molarity as a tool. Molarity. Molarity means moles of solute per liter of solution. And I said you can use something like moles per liter to go back and forth between moles and liters. But the way it works is it's kind of got this triad thing going on. So if you know 2 of any of these are 3 things about a solution. In your solution, you have a certain number of moles. In your solution, that solution has a certain volume, and your solution has a certain molarity. If you know any of those 2 things, you can get the 3rd thing. It's a beautiful thing. And that's what we count on in aqueous solution stoichiometry problems. So let's just jump right in there. These are balanced, and actually on your test Thursday, you guys are going to balance several equations by yourselves, okay, for credit. And then I'm going to give you several balanced equations and ask you to do things with it. So I will give you this one balanced. Okay? So here's the question. What volume of 0.235 molar NaOH is needed to react with 35.0 milliliters of 0.108 molar H₂SO4? Now, what I would do, honestly, when I'm working these, is I take the word or the number and I put it underneath what it goes to, and things kind of fall into place. So, what volume? So this is NaOH. So I find my NaOH. I put question mark volume. What volume of 0.235 molar? So that must also be my NaOH. What volume of 0.235 molar NaOH is needed to react with? I'll switch colors here. 0.35 milliliters. That's H₂SO4, isn't it? Sorry, 35.0 milliliters of 0.108 molar H₂SO4. 0.108 molar. And then what I tell students is the thing you know the most about is the H₂SO4. The thing you're trying to find something about is the NaOH. You are honestly going to start with what you know most about. Okay, so here in a minute, do you see where we can use the volume and the molarity to get to moles? That's what the previous slide said. If we know volume, 35.0 milliliters, if we know molarity, 0.108 molar, we can get to moles. And that actually is going to be our first step. Step number 1, in this case, moles H₂SO4. Now, if we have moles of H₂SO4, do you see where we can use the stoichiometry to get to moles of NaOH? The whole 2 moles of NaOH will react with 1 mole of H₂SO4. That's the stoichiometry part of solution concentration, stoichiometric calculations. So that's all I'm going to do. Next one, step number 2, I'm going to get to moles of NaOH using stoichiometry. Well, let's just say we have the moles of NaOH now. Do you see where I can use the moles and the molarity of the NaOH to get to volume? That's it. Step number 3 in this one. And I vary a little bit. Get volume of NaOH using the moles. And it's always using the moles I got from step number 2 and the volume. Oops, and molarity. And of course the molarity, if you've done it the way I did, you see what the molarity is because it's sitting right underneath your NaOH. That's it. They're very, you'll see, we'll do kind of another different one coming up. Okay. So what you just saw is basically we have two kind of solution problems that are joined in the middle by kind of a stoichiometric calculation. And I like to actually, you can string these up, but I like to kind of break them up into 3 problems anymore. Because if you string them up, you have to be extra careful about writing the species, whether it was H₂SO4 or NaOH. If you do them separate, you can actually just kind of label the calculation. And usually I will label my calculation. Okay, so these 3 steps are the 3 steps I talked about a minute ago. Step number 1, what do you know the most about? Well, it's the H₂SO4. You know volume and molarity. So you can get to moles of H₂SO4. Then it's always going to be a pattern of using stoichiometry to get to the moles of the other thing. And once you have the moles of the other thing, since we had molarity, we can go moles and molarity to get to volume. That's it. Okay, so like I said, I like to label these things. And these are problems that you guys have been handing in, over the last week or so. So you guys have been doing these. How many moles of H₂SO4 are there in that volume and that molarity? Well, you're going to have to unpack that molarity. I should never see your problems with a capital M in them. That's moles of MOL, H₂SO4 per 1 liter of solution. So our first term is going to be that 35.0 mils over 1. And since I want to use, I bet you guys will buy this. If I have unpacked this, and I probably would unpack it, 0.108 moles of H₂SO4 per 1 liter of solution. If I've unpacked that, I recognize that I can't use that right away because I have milliliters and I need liters to use molarity. So that's why in a lot of these, if they're given milliliters, which you are a lot of times, you're going to have to convert that to liters next. So now my milliliters have canceled. Now I have liters. So now I can bring down the molarity. And that should give me moles of H₂SO4. So milliliters have canceled. Okay, liters have canceled. Okay, and I have units of moles of H₂SO4, which is what I was trying to get from volume and molarity. Rounded to 3 significant figures. We have ready to go on to the next step. We have the moles of H₂SO4, 0.00378 moles of H₂SO4. So now, if you label it like I like to label it these days anyway, if you label what you're trying to do, you don't have to put in 35 milliliters of 0.108 molar H₂SO4, but if you label it moles of H₂SO4, then you don't have to do the other explicit labeling. You can be a little bit more abbreviated, but you have to show me what you're doing. Okay, so the second step is now we're trying to get to moles of NaOH. For this one, we need the balanced chemical equation. So we talked about, we can come up with a stoichiometric ratio between what we know and what we're trying to get to. So to me, it looks like 2 moles of NaOH per 1 mole of H₂SO4, and that's exactly what we're going to do. So we're going to carry that number from our first calculation, 0.00378 moles of H₂SO4, put it over 1, and then simply we're going to put the 2 moles of NaOH over 1 mole of H₂SO4. So you see where those numbers came from. Those are stoichiometric coefficients. Okay, so this came from here. Okay, and this came from here. So there's no uncertainty brought by the coefficients, so it looks like 0.00756 moles of NaOH. So now we know enough about our NaOH where we have the question mark volume. Okay, so now we know moles and we were given molarity. So step number 3 will piggyback on these moles. You'll see the 0.00756 moles of NaOH again. We need to double check what the molarity of the NaOH we were given. So we want moles to cancel, we want to be left with volume. So can you see we're going to use the flipped version of the molarity. So there's the molarity that was given in the problem. 1 liter of solution for 0.235 moles of NaOH. So we'd be done. Now, some part, because moles will cancel, we'd be left with liters of solution. Question mark, volume of NaOH, we're totally done. Sometimes they'll want volume in milliliters though. And so actually I went ahead and added this last term here. I can't remember, I don't think it said volume in milliliters. Would have been done with the first 2 terms, but let's go ahead and have liters cancel. We'll be left with units of milliliters. Okay, 3 sig figs. And there you go, 32.2 milliliters of solution. It's a titration problem. Okay, let's do one more. Okay, so like I said, you're going to see me pull out information and put it under what it matches up with. I just think that's a good route to go. A lot of chemistry problems, that can be helpful. Even your just regular stoichiometric calculations, it can be helpful. So what is the concentration of, so question mark, molarity. What is the concentration of an H₂SO4 solution if 25.0 milliliters of the solution, that means the H₂SO4. So I'm going to put 25.0 milliliters under my H₂SO4. We have 25 milliliters of solution required, and then it gives me a volume and molarity of the NaOH. So the volume of the NaOH is 27.7 milliliters. And the molarity is 0.444 molar. So here it's different. What you know most about is your NaOH. So step number 1 is going to be to get to moles of NaOH. And step number 2 is to get to moles of the other thing, H₂SO4. That will be our stoichiometric ratio. I'll just put stoic ratio. And then if we have the moles of the H₂SO4, notice that we can take those moles, divided it by that volume to get molarity. I'll just put M of H₂SO4 by taking moles H₂SO4 from step number 2 divided by volume, which was 25.0 milliliters. So that's the strategy. So steps 1, 2, and 3. All right. So execute. Step number 1, from the thing we know the most about, we have volume and molarity. We can go ahead and get to moles. So I'm going to put the 27.7 milliliters over 1. Since I want milliliters to ultimately cancel with liters, they wouldn't. So I need, the next term actually is going to be my 1 liter over 1,000 milliliters. And then the third term is going to be my molarity. Remember what 0.444 molar means. 0.444 moles of NaOH per 1 liter of solution. So if I use the unflipped version of the molarity, then let's make sure what cancels. Usually before you put anything in your calculator, you should just make sure that your units are good. Milliliters of solution cancel, liters of solution cancel, and we have moles of NaOH. Looks good to me. So 3 significant figures, 0.0123 moles of NaOH. So now we have moles of NaOH. We need to get to moles of H₂SO4 for the second one. So we'll piggyback Our first term here is going to be that 0.0123 moles of NaOH. There's where we need to glance down at the balanced equation. So we're going to have moles of NaOH cancel, so we're going to put 2 moles of NaOH in the bottom and 1 mole of H₂SO4 on the top. So moles of NaOH cancel. We're left with moles of H₂SO4, which is what we wanted. There's no uncertainty brought by the 1 or the 2, so we still have 3 sig figs. So 0.00615 moles of H₂SO4. And we're almost done. So now we can use those moles, and we're after molarity. So the sample aliquot was 25.0 milliliters. So if you just take those moles over the 25.0 milliliters, of course, if the units there aren't molarity yet, okay? So to get molarity, we need to fix the bottom from milliliters to liters. And the way we do that is to put 1,000 milliliters over 1 liter. That's the next term. So if our target was to get the molarity of H₂SO4, looks like we've got it. Milliliters of solution cancel. We're left with moles of H₂SO4 per liter of solution, and that is molarity. Round to 3 sig figs, 0.246 moles H₂SO4 per liter of solution. So you kind of see where it looks like there's 2 things. There's volume and molarity, and one of those, or I guess that's 4. There's 4 things, and one of those things you won't know. So let's take a look at these then. These are like the last slide, so we're going to skip all that other stuff. These will also be due on Wednesday. So let's take a look. 1391, 93. You guys know I push these out to the Twitter feed, so you can get these from the Twitter feed if you want them. These hints. So here's what 91 looks like. I went ahead and in blue and in red kind of extracted the information from the problem and put it under the thing we know or is associated with. So you see where we know more about the nickel 2 chloride. So the strategy, the strategy is going to be to get the moles of the nickel 2 chloride.
Screen it black.
I know, thanks. From what you're given. So you calculate the moles of nickel 2 chloride from volume and molarity. And you will need to convert from milliliters to liters. Then calculate the moles of K3PO4. In fact, I even use this, put you the stoichiometric ratio you'll be using. And then you'll calculate the volume, which is what you're after, question mark volume. Now you have the moles and molarity. And the next one. Okay, you can kind of see what you're given. And so what you know most about is the potassium hydroxide. We can get moles from volume and molarity of the potassium hydroxide. We can use the stoichiometric ratio then to get from moles of KOH to moles of H3PO4. Once we have moles, we can use moles and volume to get to molarity. So that's kind of how that works. Okay. I want to show you one more thing before we go. I'm going to show you a little video, hopefully, of a titration.